Okay, so the question that may be burning its way into your head is, what happens if I don't know sigma? Well, a couple things. This gets a little tricky because if you think about this for a second, if you don't know what sigma is, all right, if you don't know what the population standard deviation is, and this happens often in research, a lot of our assumptions start to break down. Now, one of two things, we have to deal with two separate issues, all right? The first thing that we have to deal with is what is the distribution, of the population, all right? Now, the first, what is distribution of pop? And if the answer to this is it's a normally distributed population, if the answer is this, then we're in pretty good shape. We have a whole lot of room to wiggle. All right? If it's unknown, or it's not normal, then our constraints get a lot tighter. Okay? And we will get into this here in just a sec. But for now, what I want you to understand is that I don't know what sigma is. But I will be able to determine what S is, because I mean, give me any sample of data, of numerical data, and I can tell you what S is. I can just calculate it. It's no big deal at all using our formula. Remember the square root of the sum of x minus mu squared. Remember, S squared is equal to the sum of x minus mu squared divided by n minus 1, which implies that S is just the square root of S squared, or this guy. Nothing to it. So you give me any data set and I can come up with a sample variance, okay, and a sample standard deviation. Now, remember, I know that z is equal to x bar minus mu over sigma over root n. This is called the standard error of the mean. However, if sigma is unknown, now, I'm going to introduce a new term. It's called a studentized t, or a student t. This t right here is called a student t. All right? And what it is, it's exact what it is, I hate that. It's exactly the same formula. The only difference is that we get rid of the sigma and we replace it with an s. All right? However, the table that we use is different. And the reason that the table that we use is different is because if I don't know what sigma is, or I don't know what the distribution looks like, then I'm in a great deal of trouble because the central limit theorem starts to break down. Remember, this thing was produced as a result of the central limit theorem. That said, if I take a sampling distribution, then the distribution of the means starts to look normal. But if I don't take a big enough sample, right? Okay, sometimes it's not practical to go out there and collect 800 pieces of data. Let's say that n is only, if all that I can get is, I don't know, n equals 15. So I'm only gathering 15 pieces of data. Well, the question that you have to ask yourself is, what does that mean as far as, is that big enough to start using the central limit theorem? All of this was based on the central limit theorem. This might not be a big enough number for me to be able to do that. So what we use is called the studentized t table, and I'm going to show you that real quick because some interesting things are going to happen with that. Let's get into this guy right here. All right, this is, where's my student t table? That's not the one. Where is that guy? Oh, sorry, I'm in the wrong one. All right, if I go up here, this is the table that I'm going to use instead of using the standard normal table. Now, the thing that I want you to notice first and foremost, the thing that's absolutely most important, is called the degrees of freedom. And we've talked a little bit about these, but now it's officially it's time to start really talking about this. So let's talk about degrees of freedom. All right, degrees of freedom, which is always abbreviated as DF. Freedom, all right, which is DF. Now, for a T situation, which is what we're talking about right now, DF is always n minus 1. And the easiest way to describe what degrees of freedom is, think about this. If I am trying to take the average of a data set, so let's say that I'm trying to figure out what X bar is, and I know what one of my data values is. I know what this number is, okay? Then, if I know what this number is, and I'm trying to get to a specific mean, remember, this would be the sum of x1 plus x2 plus x3 plus dot 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 plus x sub n divided by n, all right? Now, let's say that I know what this guy is right here. If I know what, basically I have fixed one data value, then what that tells me is, since there's a total of n data values in this thing to be able to find the mean, there are n minus 1 degrees of freedom, because I've subtracted out this known value right here. So if there are 12 and I know what one of the data values are, then there are 11 degrees of freedom. In other words, the other data values, the other 11 data values can roam. They can basically be whatever they want to be, okay, for a fixed mean. If there are 100 data values and I know what one of them are, then there are 99 degrees of freedom. Now, that's not a great way to describe it, but to be honest with you, the definition in the book is as follows. The degrees of freedom for a collection of sample data is the number of sample values that are allowed to vary, that are allowed to be as free as they want after certain restrictions have been made. Well, the certain restrictions are that I know what one of the data values are, and I know what the mean is. All right? So these guys are allowed to roam all that they want. Now, we're not going to get too wrapped up in this. This is not an introduction to statistics course topic. Excuse me, I'm going to take a drink. However, we are going to have to use it. Now, the one thing that you have to know about a t-distribution versus the z-distribution, which is the standard normal curve, is that what happens with the t-distribution is you get a family of curves. And what this family of curves looks like is this. Let me show you this real quick. Whoops. Wait, I got to get on here and back out. Get rid of you. All right, now look at this. So this is the family of curves right here. It's just a couple of the curves, but I want you to notice a couple of things. When the degrees of freedom are infinite, in other words, when I gather a whole big bunch of data values. Now think about that. If I gather a whole bunch of data values, then there's no doubt about it, and I take the average, then the central limit theorem is going to take over, and what we end up with is your standard issue, standard normal curve, which is what we like. All right, or a normal curve, which can then be translated using the z-score. However, look at what happens. As my degrees of freedom decrease, then when degrees of freedom are 6, look at this curve. It flattens out the normal curve. It's as though somebody stands on the top of it and pushes it down. All right, and the reason that it does that is it pushes out these tails a little bit further because we're not as confident. We're not as confident that it's a perfectly normal curve. So we push these guys out, and the reason that we do that, wait, let me show you what happens. So if I'm talking about 1.96 and negative 1.96, remember those for our confidence intervals, those were the confidence intervals, those were the values, the critical values for building those intervals. When degrees of freedom were 6, look at what happens. They get pushed out to 2.45. Now if you think about that, what that does is it takes our confidence interval that may be this size. I know that I'm being silly in the way that I do this, and that because of the formula for the confidence interval, it makes it bigger. If degrees of freedom are even smaller, look at the difference. For a normal curve, for the z, it was 1.96. If my degrees of freedom are only 3, that means that my sample size is 4, right? Because degrees of freedom are always n minus 1 for the t. Now I'm way out at 3.18. So in other words, to be more confident that my confidence interval actually contains the mean, I have to grow the interval. I have to make the interval bigger. Does that make sense? The smaller n is, if I want to build a confidence interval, then the bigger I have to make that interval. Okay, I got to make it wider. It's like, oh man, this interval is too small, and I don't know what sigma is. Remember what sigma is. It tells us how variable the data is. If I don't know how variable the data is, that means that there can be wild swings in the data, which means that for me to be able to capture the true population mean, then I'm going to need to build this guy out. I can't have him be in this little guy right here. Whoops. I can't have him be in this little guy right here that's created when, remember back when my z alpha over 2 is 1.96. right? When my degrees of freedom are less, when in this case it's 6, which means that n is 7, I have to build this guy out to be more confident. All right, I hope that explains that. We'll get a lot of practice with degrees of freedom, so don't panic. All right, now let's go back to, let's go ahead and use our formula. We're going to play with this thing. Now remember, if I'm talking about a standard issue, if I'm talking about a standard issue confidence interval with around the mean, I know that I end up with x bar, and this is going to be minus z alpha halves times sigma over root n, and it's going to be x bar plus z alpha halves times sigma over root n. All right, now remember, this guy right here is the error on both sides. And the algebra that we did, remember, if I start with t equals x bar minus mu over s over root n, then the algebra that I'm going to do to get the exact same interval is going to be exactly the same. All right, it's going to be x bar minus t alpha over 2. Remember, the curves are still very normal looking. T alpha over 2. I don't know sigma, so I'm going to use s, and I'm going to divide by the square root of n, and then I'm going to get x bar plus t alpha over 2 times s over root n. This has now become our error term. Now, the tricky part about this is now we have to, if we don't have a sample standard deviation, then we have to figure it out. We have to plug it into our calculators, and we'll do a ton of that in this class. But really look at it. It's almost the same formula. The only difference, and I'm going to highlight this by changing colors, the only difference is that we have to use our degrees of freedom to find this value right here. And the degrees of freedom in this case is always n minus 1. And that helps us find this guy. So I'm going to walk you through one of these right now. We'll go through the whole process from start to finish. We'll build the confidence interval, and then we'll just kind of explore the difference between these two confidence intervals and really what they mean. All right? All right.